Hello students. In today's class we will be summarizing our chapter number 3. So I'll start the class with the points. The very first point is saying that current through a given area of a conductor is the net charge passing per unit time through that area. So what is the definition of current? Current is generated basically due to the motion of charges. Okay? Current generated due to motion of charges. So amount of current, if I want to find in this cross-sectional area, I should know how much of charge is passing through and within a given time. Okay, within a given time. So the equation which we give when we are defining our current equals to charge upon time. Basically we can say that rate of flow of charge is current. Rate of flow of charge through a given area is current. Okay. Now moving on to the point number 2. To maintain a steady current, we must have a closed circuit in which an external agency moves electric charges from lower to higher potential. So, we are talking about the steady current. There are two kinds of current. The way we have read about the fluids in 11th standard, similarly, the current, sometimes current is not uniform and sometimes it is uniform. The uniform motion of charges is known as steady current, and whenever charge is not uniform we will say that this is causing the destruction in the environment. We have seen the example of thundering. The thundering is an example for our non-uniform current or unsteady current which causes much of natural calamities. So to maintain this steady current we should have a closed circuit. Closed circuit is very much important for the flow of charges, then in which external agency moves electric charges from lower to higher potential, like uplifting from lower to higher. Here we have less charges and here we have less potential and here we have higher potential. Our charges will move in this direction and this will create the current. The work done per unit charge by the source in taking the charge from the lower to higher potential energy from one terminal to the source to the other is called the electromotive force or EMF. Like whatever amount of energy is needed, whatever amount of work we did on this charge Q to make it move from the lower potential to the higher potential region, that work done is known as electromotive force or EMF. The note over here is EMF is not force. It is the voltage difference between the two terminals of a source in open circuit, VA minus VB or V lower minus V higher. Moving on to the third statement, that is Ohm's law. Ohm's law is a very important law whenever we are reading the electricity and the electric currents and circuits. Okay. The electric current I flowing through a substance is proportional to the voltage V across its end, that is V proportional to I or V equals to Ri. Now what is R here? R is the resistance of substance and it is also constant of proportionality. Constant of proportionality. The unit of resistance is ohm. It is written as a capital U with two arms, or we can write as 1 volt per ampere, because V equals to Ri, then R equals to V upon I. So if we know the value of either the voltage and resistance, we can find the value for current, or vice versa. Like if we are known to the two things here, we can find the third with this relation. Now moving on to the next slide. Point number 4. The resistance R of a conductor depends on its length and cross-sectional area A through the relation R equals to rho L upon A, where rho is resistivity. It's a property of material, depends upon temperature and pressure. If temperature and pressure is changed, the resistivity for a material will change. Now we'll decode this relation. R equals to rho L upon A. This relation says that R is proportional to L upon A, which says that R will increase in case L is increasing, but R will decrease in case A is increasing. What basically it means, if length of a wire is increased, then resistance will increase. But if area of wire is increased, then resistance will decrease. Okay, so this is the relation. It's very much important. Here we have understood the relation of our resistance with respect to length and the area of the material. Secondly, we are exposed to a new terminology, that is rho, 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 which is the symbol for resistivity. Resistivity is a property of a material. It depends material to material. Resistivity of our iron will be different than the copper, then the gold and silver. Like it will differ from the material. Then after being dependent upon material, if that material is on lower temperature, it will have different resistivity. If that material is on higher temperature, it will have different resistivity, and same goes with the pressure. It do changes with pressure. Now point number 5. I have given little more importance to the number 4 point because it is quite important. You have to make it into a short note for your examinations. Okay, so now the electrical resistivity, will go to the point number 5, of substance varies over a wide range. Metals have low resistivity in the range of 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter. Resistivity, if they are having less resistivity, then only they will allow more flow of current. Allow more flow of charges, hence more current. If they are resistive for the charges flow, then how will current gonna produce is a question. So metals, as they are very good in conducting, they have low resistivity, but high conductivity. Okay, high conductivity. Make a note. Insulators like glass and rubber have 10 to the power 22 to 10 to the power 24 times greater resistivity. That simply says they have lower conductivity. They do not allow motion of charges that freely. Now semiconductors like silicon and germanium lie roughly in the middle range of resistivity on a logarithmic scale. Now it totally depends upon the dopant we are using in semiconductors, the impurities we are adding in some semiconductor to make them highly conductive or less conductive. But semiconductor lie between these two ranges. Moving on to the sixth point. In most substance, carrier of currents are electron. In some cases, for example, ionic crystal and electrolytic liquids, positive and negative ions carry the electric current. Basically here, the statement is saying that in elements or in the solids like wire and all in our electric circuits, if mostly we see the charges are electrons which carry current, but when we are considering a chemical solution or a chemical ionic crystal, in such a case negative and positive ions both show, both these ions show that they carry electric current. Now one more important thing which needs to be understood over here is, in case of these semiconductors also, we will have minority carriers and majority carriers, which in detail we will be discussing in chapter number 14 of our 12th standards syllabi. So there are minority and majority charges. In that we take electrons and holes. Holes are apparent positive charges whereas electrons are negative charges, and both in different situation carries the current. So this is also an example where not just electron but others are also carrying the currents. Okay. Moving on to the seventh point, current density, which is given by the small letter J, gives the amount of charge flowing per second per unit area normal to the flow. Okay, so it is given by J equals to NQVD, where N is the number of charges, and Q is the charge, and Vd is drift velocity. See here, N is the number density, number per unit volume of charge carriers, each of charge Q. Vd is drift velocity of these charge carriers. For electrons, Q equals to minus E if J is normal to a cross-sectional area A and is constant over the area. Magnitude of current I to the area will be given by NEVDA. NEVDA, that is number per unit volume charge into drift velocity into the given area. Now we have this 8th point. For using E equals to V upon L, I equals to electric field applied equals to potential upon the length of the circuit wire, where I is the current flowing, which is given in terms of drift velocity as NEVDA. See over here, this is the equation, and we have applied the Ohm's law for correlating V and I, that is potential and current. EE, that is charge and electric field divided by mass, equals to rho into NE square upon MVD. And upon solving, we will find VD equals to A tau, which will be equals to EE tau upon M. Here A is equals to EE upon M. From here we can find the value of A. The proportionality between the forces EE on the electrons in a metal due to external field E and drift velocity Vd, not acceleration, can be understood if we assume that electrons suffer collision with ions in the metal which deflect them randomly. If such collision occurs on an average at a time interval of tau, then we know that acceleration equals to velocity upon the time. The time for collision is given to be tau. So for Vd we will have A into tau. Now from here we can find the Vd and the value we can substitute over here, where A is the acceleration of the electrons and this gives us the value of resistivity. For that particular material, which is rho equals to M upon N E square tau. Now the ninth one. In the temperature range in which resistivity increases linearly with temperature, resistivity is increasing linearly with temperature. The temperature coefficient of resistivity alpha is defined as the fractional increase in resistivity per unit increase in temperature. This is alpha, that is coefficient of resistivity, and the equation corresponding to this is given RT equals to R naught into 1 plus alpha into delta T. So here RT is the resistance at a given temperature, R naught is resistance at room temperature, 1 plus alpha is its coefficient of resistivity, and del T is change in the temperature. This equation can be written with respect to the resistivity as rho T equals to rho naught into 1 plus alpha delta T. Okay. So this shows that there is a fractional increase in the resistivity per unit increase in the temperature. This is the equation for this statement. We'll move. Point number 10. Ohm's law is obeyed by many substances, but it is not a fundamental law of nature. It fails if our potential depends upon current non-linearly. Like if potential is increasing, our current is either increasing very fastly or slowly, but not equally. In such a case, Ohm's law fails. I'll give you a very simple and understandable example. Like you are studying 3 hours a day and you scored 40 marks out of 100. Then you started studying 4 hours a day and you scored 60 marks. So basically for 3 hours 40 marks, for 4 hours 60 marks. Now what you did, you started studying for 5 hours and you scored 80 marks. Then 6 hours and you scored 100 marks. This is linear. You increased 1 hour of studies and your marks increased by 20. 1 hour again 20, 1 hour again 20. But in case this is not happening, like you are very intelligent, in that case if you are studying for 3 hours, you scored 40. You increased to study for 4 hours and your marks increased to 80. And then you studied only for 4.5 hours and there is an increment in your marks from 80 to 100. So it is not too much linear. But in this case, it is very much linear. If such linear cases are there, then Ohm's law is valid. But if such a case is not there, then Ohm's law is not valid. In this second case, Ohm's law is not valid. So this is one of the very much important point to remember. Now second, the relation between V and I depends on the sign of V for the same absolute value of V. What it means is potential should be same every time to get a same current. If our charges are moving from 15 volt to 20 volt, we will get some current I. Similarly, if charges are flowing from minus 15 to minus 20, here again we will see that this is lower, this is higher. But in this case, this is higher and this is lower. We will not get the same I. If potential sign is changed, if the circuit is reversed, in that case we won't get the same current. There is a device known as commutator. Commutator. You people can share the reviews about commutator here in the comment box also. But still, for the other people who are not curious enough to know what it is and are not ready to go and check the Google, I'll tell. Commutator is a device, electronic device, which we use in our circuits in our physics laboratory to change the direction of current. Here also we are changing the direction of current but not the voltage. So how this direction in current, like change in direction in current, is happening with the help of commutator can be read later on. As of now, just want to make sure that you people know the device. Here, as we were discussing, the sign change of the voltage, which is also showing a great impact on the magnitude of current. Now the C point, relation between V and I is non-uniform. Of course, it is like V equals to Ri. Somewhere it depends upon the resistance of that material too. So it is not exactly uniform. An example of A where rho increases with I, even if temperature is kept fixed. A rectifier combines feature A and B. GAS shows feature C. I'll make you understand. A rectifier is a device which rectifies the beam. Like if we are giving it a sine wave, it takes all the positive value and leaves up the negative value. So just mark this point rectifier. I'll explain in the end of this slide. Okay, I'll also mark it up. because it is very much important. We will be reading this rectifier in our last chapter of 12th syllabus, that is semiconductors. These two chapters are very much linked. You will be reading it, but for today I'll just give a glimpse of it to you all. It combines the feature of A and B. What is A? A says that V and I depends with each other non-linearly. Second, it is that I depends upon the sign of voltage. Okay. Now GaS is gallium, which is doped with this As. It shows the feature of C, that is relation of V and I is non-uniform. This will be shown by GaAs, where if a little voltage is increased, you will see that current is increased very much, like this. Okay, a point will come till that if you are increasing the voltage, current will increase. Then slowly, if you are increasing the voltage, our current will start reducing and then it will stay constant. At the end, the current will stay constant. Okay. So that is the feature number C. Moving to next point 11. When a source of EMF E is connected to an external resistance capital R, the voltage V external across R is given by V external equals to IR equals to E upon R plus R into R. Current equals to voltage upon the resistance. Okay. So here this is the EMF, that is the voltage inside the circuit, and R plus R is the internal resistance plus the externally added. See, where small r is the internal resistance of the source. Now we have Kirchhoff's rule. Kirchhoff gave us two rules, junction rule and loop rule. I have explained both the rules twice. Once when we were dealing with Kirchhoff's rule, second time when I was taking one example problem for you all. So once again we will just refresh what we have read so far. A is the junction rule. Junction rule says that at any junction of circuit elements, the sum of currents entering the junction must be equal to the sum of currents leaving it. Current entering equals to current leaving. Okay. Then the loop rule. Algebraic sum of changes in potential around any closed loop must be zero. If this is a circuit having the batteries, the resistance, so in this case if we will apply loop rule, all the V plus V1 plus V2 plus V3, everything will give us 0. All the changes when summed over will give us 0. Point number 13, it's about the Wheatstone bridge. It's an application or an example of our Kirchhoff's rule. Is an arrangement of 4 resistance R1, R2, R3 and R4. The diagram is like this. There is a galvanometer attached here diagonally, and the other diagonals are added with an external EMF source. R1, R2, R3, R4. If a situation arises when the current flowing through this is 0, then this terminal is nullified and we will have R1 upon R2 equals to R3 upon R4. Using the Wheatstone bridge and its formulae, this one, we can determine the value of any one unknown resistance if we know the value of remaining three resistance. Another thing in practical uses, to know the resistance R4 which is unknown to us, we add R1 and R2 which are known to us, and R3 is a rheostat. Rheostat is an electrical equipment which gives us variable resistance. Okay, variable resistance. Using this rheostat, we can vary the resistance, and we will keep on varying the resistance until R1 upon R2, the ratio of R1 upon R2 equates the ratio of R3 upon R4. Once the ratio is equal, at that point, we can find the value of R4. Okay. This is also one of the way to find the variable resistance and the unknown resistance, and this is practically used in another equipment known as potentiometer. Potentiometer. Now we will discuss few units, and then at the end I'll give a glimpse of what is a rectifier. So here we have these physical quantities. These are the symbols. These are their dimension, unit and the remarks. Electric current I is given by A, that is the dimensional unit. Its unit is A, that is ampere. It is a SI base unit. Charge is given by capital Q or small q, which is charge Q equals to I into T, because I current equals to Q upon T. Okay, so it is T and A, given by coulombs. Then we have voltage or electric potential difference, which is given by V. Its dimension is mL2 T minus 3 A minus 1. It is work upon the charge. Electromotive force denoted by epsilon. Epsilon, which is given by V. It is also work upon charge. Same dimensional units as the potential difference. Now we have resistance and resistivity given by R and rho respectively. Resistance dimension is M, L2, T minus 3, A minus 2 given by ohm, and its formula is R equals to VI. Resistivity is M, L3, T minus 3, A minus 2 ohm meter. Ohm into meter given by R equals to rho L upon A, or rho equals to RA upon L. Electrical conductivity is given by sigma. Its dimension are M minus 1, L minus 3, T3, A2. It is opposite of resistivity, and the value, its unit is given as Siemens. It is Siemens, and sigma equals to 1 upon rho, that is reverse or reciprocal of rho. Then electric field E, it is mLT minus 3 A minus 1 volt per meter. It is given by electric force upon charge, that is KQ1 Q2 upon R square into the charge Q1. So it will get cancelled out, giving us KQ upon R square. Okay. Now we have drift speed, which is given by Vd, that is L T minus 1, same meter per second. Okay, Vd equals to E tau upon m. Here small e is the charge on that particular charge, and then E is electric field, tau is relaxation time over here, and m is collision time basically, and m is the mass. Now relaxation time tau equals to T given by second S. Current density is given by a small letter J. It's a vector L to the power L minus 2A. It's given as ampere per meter square and current upon area. Mobility is given by mu. It is ml3t minus 4a minus 1 meter square v minus 1 s minus 1 given by vd upon a, that is drift velocity divided by the electric field. We'll just see the concept of rectifiers. Okay, so the rectifiers do rectify wave, and it's a concept which we will be reading in our chapter 14. So it is a device having diodes. When we are having a wave like this is the positive half of the wave and this is the negative half of the wave. When this wave is allowed to pass through a rectifier, this rectifier allows only the positive half of the wave to pass through it. That is half wave rectifier. Okay. Now because here the voltage is being changed as this, V and I are non-linear. Second, if sign of V is changed, I won't remain same. So in this case the sign of the voltage is reversed. So there is no production of this wave, but it's producing this one wave. Now to just overcome this, we came to another new device that is known as full wave rectifier. This device rectifies the whole wave, let it be positive or negative. Positive, negative, positive, negative. It's allowed to go through the rectifier. What we're gonna receive over the end is only positive. Only positive. So this is the example which is justifying the option number B, and this is what the rectifier do. In detail, how the rectifier is made, how this is happening, we will read in our chapter 14, semiconductors. Okay. For the time being, have a good day, prepare well, do study, and just enjoy reading the physics. Bye bye.